In this video, I will show you how to solve integrals using a U-substitution. First, we have to ask ourselves what is a U-substitution. Some integrals you can solve directly, but some integrals are trickier. These integrals you will have to change somehow in order to make them easier to integrate. These integrals you can make look cleaner by introducing the U-substitution in a way which is peculiar to that specific integral. In order for me to show you how that works, we are going to look at these integrals. These are all the types of problems which I am going to show you how to solve using the U-substitution in this video. The first integral is the most basic one. And in this integral, we also have a power rule. The second integral has a fraction and a square root, and you will have to manipulate the du expression to get what you need to be able to integrate. Here we'll have to divide by a number, and that will be a negative number. The third integral has a square root, and you will have to manipulate the du expression by subtracting a number in it in order to make the integral easily integrable. The fourth integral has trigonometric functions in it, and it is also a fraction. Here you will also have to rearrange the du expression in order to make integral easier for solving. That is enough talk. Let's now solve these integrals. The first thing you are going to do when solving an integral is to determine what is an area in which that integral is defined. For this integral, it is obvious that it is defined in the set of all real numbers. Now, when you take a look at this integral, the first thing that comes to mind is to expand the entire polynomial of the 7th power and then multiply the entire polynomial by this 3x squared. And then separate this integral into a bunch of simpler integrals which are all table integrals and solve them one by one. That is a long and painful process which I would recommend avoiding at all costs, even though it is something that you can do. Far better method or approach to this integral is to use the U-substitution. The only reason why this is called U-substitution is because we are using the letter U. Instead of the letter U, you can use any other letter you want. It really doesn't matter. By using the U-substitution, we are going to rewrite this entire integral in terms of the variable u. The first step is to decide which term we are going to substitute with u. With problems like this one, a good rule of thumb is to pick the expression of x which is longer or which has a higher degree of x in the integral. That can also be an expression which in some way is involved in a composition with some other functions. In this case, the expression x cubed plus 5 is entangled with a power function as it is being raised to the power of 7. In general, that can also be a square root or a denominator of a fraction. When using a U-substitution, an important fact that will always remain true is that the integral will have some function and the other part of that integral will be the derivative of that function. Notice here that the derivative of x cubed plus 5 is equal to 3x squared, and you already have 3x squared here. This gives you an intuition that you should pick for U-substitution this term x cubed plus 5. The next step is to find the differential of u, that is du. Du is derivative of u function in respect of x multiplied by the differential respectful of x. This is equal to x cubed plus 5 as that is u multiplied by the differential of x, and this is 3x squared. Remember, the derivative of a constant is 0, so we are going to have just this 3x squared multiplied by dx. In these easier problems, your du will be exactly what you have remaining in the integral apart from u. This integral then gets transformed into u to the power of 7, x cubed plus 5 is u, so you have u raised to the power of 7, and 3x squared dx is what corresponds with a differential respectful of u. As you can see now, an entire integral is written in the respect of the variable u. As you can see now, you have a table integral where u is raised to the power 7. By using the power rule, we get that this integral is equal to u to the power of 7 plus 1 divided by 7 plus 1, and then we are going to add an arbitrary real constant c. So this is equal to u being raised to the 8th power divided by 8 plus c. And now that we have done the integration, you can notice that our original integral was given in the terms respectful of the x variable. And now we have the result in terms of the variable u. This means that we are not done yet. We have to return our substitution now in order to get the final result in the terms of x, the same way as our original integral was given in the terms of x. We are going to plug in here our U-Substitution. U is equal to x cubed plus 5, so this is x cubed plus 5 raised to the 8th power divided by 8 plus c, and this c is an arbitrary real number. So this is our final answer for this integral. Notice how the U-Substitution has made it extremely easy for us to solve this integral. Since it's not obvious how to pick U-Substitution, I want to show you some other possibilities which can occur and show you what U-Substitution will be in these cases. So the case which you are going to encounter is some function which is going to be a function of the variable x raised to a power, let's say, power 100. The next case which you are going to encounter is e raised to some function of the variable x. Another case which you are going to encounter is a square root of some function of the variable x, or 1 over some function of the variable x, where that function of the variable x sits in the denominator of a fraction. More complicated way which you are also going to encounter is 1 over a square root of some function of the variable x, or 1 over some function of the variable x, let's say that it is squared. Take a look at all of these compositions of functions. It doesn't matter which one of these cases you happen to encounter. Usually that's something which is inside another function, inside these parentheses, will in most cases be the U-Substitution. It is what you should define your U-Substitution to be equal to. Let's now focus on solving another integral from our list, x cubed divided by a square root of 1 minus x to the 4th power differential of x. The first step in solving any integral is to always find the area in which that integral is defined, the area D. For that, we are going to observe the function which is under the sign of the integral. In this case, that is the function f of x defined as x cubed divided by a square root of 1 minus x to the 4th power. Our job is to find an interval of real numbers in which this function f is defined. That will be the area in which the integral is defined. As you know, we are not allowed to divide by 0. So that immediately gives us condition that a square root of a 1 minus x to the fourth power has to be different than 0. And in order for the square root function to be well defined, its argument has to be larger or equal to 0. This means that 1 minus x to the fourth power has to be larger or equal to 0. Let's solve this mess now. We are going to square this first non-equality which we have. By doing that, we get that 1 minus x to the fourth power is not 0, and that means that x to the fourth power cannot be equal to 1. Well, that means that x has to be different from 1 and that x has to be different from negative 1. In this other case, we see that x to the fourth power has to be smaller or equal than 1. Well, that means that negative 1 has to be smaller or equal to x, which has to be smaller or equal to 1. The combination of all of these cases gives us that x has to belong in an interval from negative 1 to 1. For easier understanding, we can write that on a line of all real numbers. So we have our case that x is an interval from negative 1 to 1. The connector end is going to give us an intersection of all of these cases. X has to be different from 1, and x has to be different than a negative 1. So this is where x belongs. That is an open interval from negative 1 to 1, which we have here. So area in which our integral is defined is this open interval from negative 1 to 1. Important note here is that our integral only exists in this area D. Outside of it, our integral does not exist. When we solve our integral, the family of functions which we are going to get, that family of primitive functions, is also going to be defined in this area D, and outside of that area our solutions do not exist. Let's now continue to the next step of our problem, and that is the step of calculations. This example is important because it perfectly illustrates the cases which you will certainly encounter in which the picking of the U-substitution is not going to give you exactly what you need to integrate right away. In these cases, you will have to find a way how to manipulate U and du in order to obtain exactly what you need in order for the substitution to give you an integral that you can easily solve. We need to pick our u. Remember what I have told you about some possibilities that can happen. U is usually the x expression which is inside of another function. And good choice for u substitution in this case is 1 minus x to the fourth power. So let's write that down. Our u substitution is 1 minus x to the fourth power. If you make a mistake here in deciding what the u substitution is, do not despair. You can always go back and pick something else to be u. And there is not strictly one thing that you can pick for a u substitution. There are many options and it is up to you to decide which one you are going to go with. But there is one important fact that you always need to remember, and that is that the final result which you get at the end as a solution of an integral is independent of all the substitutions which you have made in the process of solving that integral. What that means is that the integral has only one family of functions as a solution. If you find different families of functions by using different substitutions, that means that these families of functions are the same. And if they are not the same, then you are the one who has done something wrong. At that point, you need to go back, find your mistake and fix it. Always remember that the solution of an integral is unique and it is independent of all the substitutions or any other methods that you have used in the process of solving that integral. Let's go back to our integral now. The next step is to find the differential du. The differential du you are going to get by taking the derivative of the expression you have used as a U-substitution respectful of x in this particular case, and then you are going to multiply that derivative by dx, which is a differential respectful of x, as x is the variable which figurates in the expression. So du is going to be a derivative of u respectful of x multiplied by the differential of x. What is the derivative of 1 minus x to the fourth power respectful of x? Derivative of a constant is 0, and negative x to the fourth power is going to give you negative 4x cubed. That is the derivative of u respectful of x, multiplied by differential of x. Don't forget this dx. It stands here because you have taken the derivative in the respect of the variable x. In the perfect case, this du would match exactly what you have left over in the integral. That would be x cubed dx. Unfortunately, that almost never happens. Here you have this negative 4, which is something that you don't want. You now have to make it to match up so you can plug u and du into the integral and continue solving it. After the substitution in the integral, you get everything has to be written in the terms of u and du. You can't have the previously used variable anywhere in there. We have to get rid of this number negative 4, which we don't want. We are going to do that by dividing an entire equation by this negative 4. We are then left with du over negative 4 to be equal to x cubed dx. Now we are ready to go to next step, and that is substituting everything in terms of u and du. So in the integral, we have x cubed dx, and that is du over negative 4, and we have the substitution that 1 minus x to the power 4 is u. So here we have the square root of u. A constant 1 over negative 4 can go in front of the integral, and then we have an integral of du over the square root of u. This is equal to negative 1/4 multiplied by the integral. This square root of u in the denominator can be written as u to the power of 1/2. And when we move it from the denominator to denominator, we get that negative 1/2 as the power of the u, and du remains. This is then equal to negative 1/4 multiplied by u to the power negative 1/2 plus 1 divided by negative 1/2 plus 1. That is the power rule. And we are going to add the arbitrary constant c, which is a real number here, as we are done with integration. So this is then equal to negative 1/4 multiplied by u to the power of 1/2 divided by 1/4. Plus c divided by 1/2. This is then equal to negative 1/2 square root of u plus c, and when we return our substitution, we get negative 1/2 square root of 1 minus x to the fourth power and plus c. Of course, c is a real number. Another way in which you can integrate this integral is to use a different type of substitution. We are going to use a U-substitution to be a square root of 1 minus x to the fourth power. Of course, the area in which we integrate remains unchanged. So this is then equal to 1 minus x to the fourth power to the power 1/2. du is u derivative differential of x, and that is equal to 1 minus x to the fourth power to the power of 1/2 derivative respectful of x dx. This is equal to 1/2 1 minus x to the fourth power to the power 1/2 minus 1, and multiplied by 1 minus x to the fourth power derivative of that dx. This is equal to 1/2 1 minus x to the fourth power to the power of negative 1/2 multiplied by negative 4x cubed dx. This is equal to negative 4x cubed divided by a square root of 1 minus x to the fourth power multiplied by 2 and dx. So du in this case is equal to negative 2x cubed over a square root of 1 minus x to the fourth power dx. du over negative 2 is equal to x cubed over a square root of 1 minus x to the fourth power dx. And then you would have that this integral becomes an integral of du over negative 2. And that is negative 1/2 integral of the du, and that is negative 1/2 u plus a constant c, which is a real number. So this is negative 1/2 square root of 1 minus x to the fourth power and plus c. And as I have told you, we have used a different substitution now, and still we got the same solution. I would like to recommend to you here that always when you see an integral which has the square root in it, try to use that square root as a U-substitution. In many cases that will solve your integral, but there are still cases where it won't help you. So just try it and see where it leads you to. Let's solve the next integral from our list, x multiplied by the square root of x plus 2 dx. The first thing which you have to do when solving an integral is to determine what is the area in which that integral is defined. We have a square root function here, and we know that its argument has to be a number larger or equal to 0. That means that x plus 2 has to be larger or equal to 0. That means that x has to be larger or equal to negative 2, and that will give us the closed interval from negative 2 to positive infinity as the area in which this integral is defined. A great idea here is to pick for substitution u that u is equal to x plus 2. The derivative of u will then be equal to the derivative of x. But here you are going to hit a problem. The square root of x plus 2 is the square root of u. dx is du, but this x here remains. Remember, the substitution is u is equal to x plus 2. So you are going to manipulate now this expression in order to get x as u minus 2. Then our integral can be transformed, and it becomes an integral of u minus 2 as that is x. The square root of x plus 2 is the square root of u. dx is du. This is then equal to an integral of u multiplied by the square root of u du minus 2 integrals of a square root of u du. So this is equal to an integral of u multiplied by u raised to the power 1/2 du minus 2 integrals of u to the power of 1/2 du. This is equal to an integral of u to the power 3/2 du minus 2 integrals of u to the power 1/2 du. This is equal to u to the power of 3/2 plus 1 divided by 3/2 plus 1 minus 2 multiplied by u to the power of 1/2 plus 1 divided by 1/2 plus 1, and plus a constant c. This is just a power rule. So this is then equal to 2/5 when we calculate all of this mass, square root of u to the 5th power minus 4/3 square root of u cubed and plus c. When we return the substitution, we get 2/5 square roots of x plus 2 raised to the 5th power minus 4/3 square root of x plus 2 cubed and plus c, where c is a real number. Now for this same integral, I want to show you what happens when you pick the U-substitution to be a square root of x plus 2. The domain of the integral remains unchanged. So u is equal to x plus 2 raised to the power of 1/2. du is x plus 2 raised to the power 1/2, derivative of that respectful of the variable x, multiplied by the differential of x. This is 1/2 x plus 2 to the power 1/2 minus 1, multiplied by x plus 2, derivative of that respectful of the variable x, dx. This is equal to 1/2 x plus 2 to the power of negative 1/2 dx, and that is 1/2 square roots of x plus 2 dx. Here you run into some problems. As you can see now, you have to get a connection from x to u. We are going to get that from the substitution. The substitution is u is equal to the square root of x plus 2. We are going to square this expression, and we get that u squared is equal to x plus 2, and that will give us that x is equal to the u squared minus 2. And to get this square root of x plus 2 in the denominator, we are just going to multiply by conveniently written 1. So this integral is equal to an integral of x square root of x plus 2 multiplied by 1 dx. Number 1 we are going to conveniently write as a square root of x plus 2 divided by a square root of x plus 2 dx. And I'm going to put a little star here because I will come back to this. This is then equal to an integral of x plus 2 1 over the square root of x plus 2 dx, and that is an integral of x plus 2 over 2 square roots of x plus 2 dx, and that is equal to 2 integrals of u squared minus 2 multiplied by u squared du, which is 2 integrals of u to the 4th power minus 2u squared, differential of u. This is 2 integrals of u to the 4th power du minus 4 integrals of u squared du, which is equal to 2 multiplied by u to the 5th power divided by 5 minus 4 multiplied by u cubed divided by 3 and plus c. This is equal to 2/5 square root of x plus 2 raised to the 5th power minus 4/3 square root of x plus 2 cubed and plus c, where this c is a real number. The reason why I have insisted in showing you this substitution is because you were able to get the correct solution in this case also. But there is one subtle mistake made in the process of solving this integral by this substitution. And that mistake is right here where I have put this symbol of star. As you can see at that step, we have in this integral a square root of x plus 2 in the denominator. X is equal to -2. Belongs in the area in which this integral is defined. But if you plug the value of negative 2 here, you will get negative 2 plus 2, which will give you 0 in the denominator, and we are not allowed to divide by 0. So the sign of equality here, where this star is, does not apply. And that is because this integral on the left side is defined from negative 2 to positive infinity, an integral which includes this number negative 2. And this integral on the right side of the equation is defined from negative 2 to positive infinity, an interval which does not include this number negative 2. These two intervals are not the same, so the two integrals are not the same. That is why the sign of equality does not hold. So even though you got a correct final answer in this case, the process by which you have come to that final answer is wrong, it is flawed, and that is why you have made a mistake. So even though you have a correct solution, that solution cannot be accepted. A little reminder I want to make here for you. We have two functions. We have function f of x defined as x, and we have the second function g of x defined as x squared over x. Two functions are the same if they have the same domains, the same codomains, and they have the same values dot by dot. Observe these two functions. We have here x squared divided by x. You are forced into cancelling out this square with this x, and you get that this is equal to x. From this, you are going to conclude that f and g are one and the same function, that they are equal. But that is simply not true. This is wrong. The domain of the function f is an entire set of real numbers. The domain of the function g is set of all real numbers. But you are going to exclude number 0 from it. Why? Because g of 0 is equal to 0 squared over 0. And you have the situation of dividing by 0 here, which is not allowed. So f and g are two different functions because f of 0 is equal to 0. It has a value in this dot 0. And the g of 0 does not exist. So functions f and g are not the same. Let's now solve the integral sine of x divided by cosine cubed of x dx. Again, we are first going to find the domain of this integral. We have cosine cubed of x in the denominator of that integral, and we are not allowed to divide by 0. Therefore, cosine of x has to be different from 0. Let's observe the trigonometric circle. We have negative 1 we have positive 1 at this point, negative 1 here, 0, negative 1, and 1. Cosine is read from the x-axis, and sine function is read from the y-axis. We need cosine of x. We are reading it from the x-axis. Cosine of x is equal to 0. 0 at these two dots, for this angle and for this angle here. Those angles are p half and negative p half. So x has to be different from p half plus kp, where this k is any integer. That means that our domain of the integral is the set of all real numbers. We must exclude from it dots p half plus kp, where k is an integer. Let's now solve the integral. The best choice for a U-substitution in cases like this when you are dealing with trigonometric functions is to pick for U that term which is being raised to some power, cosine cubed, it's being raised to the third power, or sits in the denominator of a fraction. Cosine cubed of x sits in the denominator of a fraction. So in this case, we are going to pick the substitution that u is equal to cosine of x. The differential of u is equal to the derivative of u multiplied by dx, differential of x, and cosine x, derivative of that multiplied by dx. Derivative of cosine of x is negative sine of x, dx remains. This integral here then becomes an integral of sine x dx. We have negative sine dx, so this is negative du over cosine of x is u, so we have u cubed. This is negative du over u cubed, which we can also write as negative u to the power negative 3 du under the sign of an integral. We can apply the power rule here and we get u raised to the power of negative 3 plus 1 divided by negative 3 plus 1 and plus some arbitrary constant c. This is then equal to negative u to the power of negative 2 divided by negative 2 plus c, which is equal to 1/2 multiplied by 1 over u squared plus c. So this is finally 1 over 2 cosine squared of x plus c, where c is any real number. If you want to practice solving integrals by U-substitution, I suggest that you watch this video next. I have solved 100 integrals in it by using U-substitution, so you can pick some integrals that you find interesting to solve them by yourself. Thank you for watching. Please like, share and subscribe to the channel as that helps me a lot.